December 2018. An X-ray telescope in orbit is watching a quiet galaxy 250 million light-years away when the light suddenly surges, 100 times brighter in a few hours. Then it fades. 9 hours later, it happens again and again. The galaxy is GSN 069, and the flash comes from the very edge of the supermassive black hole at its center. A team, led by Giovanni Minuti, reported it in the journal Nature in 2019, with a deliberately cautious name. They called it a quasi-periodic eruption. Quasi because the flares are almost regular, but never perfectly so. Every 9 hours, give or take, the X-rays climb, blaze for about an hour, then collapse back to a faint, steady glow. A factor of 100 in brightness, up and down, on a loop. In the entire history of watching black holes, nobody had recorded anything doing this. A supermassive black hole, hundreds of thousands of times the mass of the Sun, behaving like it has a pulse. These eruptions only show up in soft X-rays, low-energy X-rays that never reach the ground. You can catch them only from space, which is part of why they went unseen for so long, and why it took a telescope like ESA's XMM-Newton staring for hours to reveal the pattern. During each eruption, the gas doesn't just brighten, it heats up from around 50 to over 100 electron volts, a measure of its temperature, then cools as the flare dies away. Something is being violently heated on a schedule. GSN 069 could have been a one-off. Then astronomers realized a second galaxy, RX J1301.9 Pluto 747, had been flaring the same way, a pattern that had been hiding in years of overlooked data. The real confirmation came from eROSITA, an X-ray instrument on the Russian-German Spectre RG spacecraft. In 2021, it found 2 more clear cases, named eRO-QPE1 and eRO-QPE2. Quasi-periodic eruptions were a genuine class of object. To weigh the suspects, you need one piece of background. Around a feeding supermassive black hole sits an accretion disk, a flat, glowing whirlpool of gas spiraling inward, compressed and heated until its inner edge pours out X-rays. The rhythms vary enormously. eRO-QPE2 erupts every 2.5 hours. eRO-QPE1 takes closer to 18. GSN 069 sits at 9. Whatever the engine is, it runs at wildly different speeds in different galaxies. By the mid-2020s, the confirmed count was still tiny, under a dozen clean sources across the whole sky. Each one is precious, and each one is slightly different. They're also brutally hard to find. To catch a quasi-periodic eruption, you have to point an X-ray telescope at the same faint galaxy for many hours and hope to catch it mid-cycle. Most of the sky has never been watched that way. There's also a shape to each flare. It brightens fast and fades more slowly, ruling out anything perfectly symmetric. That lopsided rise and fall is a fingerprint every explanation has to match. That leaves the central question. What produces the eruptions? Investigators have narrowed it to a short list of suspects. Suspect 1, the disk itself. Accretion disks can be unstable. Radiation pressure and gravity fight each other, and under the right conditions, the inner disk can drain and refill in cycles, brightening and dimming with no second object needed at all. But the numbers resist. Pure disk instabilities tend to produce flares that are longer, softer, and more ragged than the sharp clockwork spikes QPEs actually show. The clean beat is hard to fake this way. Suspect 2. A second supermassive black hole, a close binary tugging the disk once per orbit. But to flare every few hours, the two giants would have to orbit almost impossibly close. The required period is off by a huge margin. 2 suspect weakened. The third hasn't just survived, it has grown stronger with every new observation. Picture a much smaller object, a white dwarf, or the stripped-down core of a star, captured into a tight orbit around the giant black hole, completing a full loop in just a few hours. Its orbit is tilted relative to the disk, so twice on every loop, it plunges straight through that sheet of hot gas at thousands of kilometers per second. Each impact blasts out a cloud of shock-heated material that flares in X-rays. Then, the object punches through, and the flare subsides. This explains a detail the other models can't. Many QPEs alternate between longer and shorter gaps. 2 crossings per orbit on a stretched, eccentric path produce exactly that uneven rhythm. And crucially, the object survives each pass. It isn't swallowed, it just keeps diving through the disk over and over, ringing the black hole like a struck bell. This suspect carries an extraordinary implication. An object that's small orbiting a black hole that closely, and that fast, warps space-time hard enough to radiate gravitational waves. It is physically a gravitational wave source, one we might be watching in ordinary X-ray light. We'd be seeing the shadow of a gravitational wave target years before any detector could hear it directly. That detector has a name, LISA, the Laser Interferometer Space Antenna. 3 spacecraft the European Space Agency plans to launch in the 2030s to catch waves from exactly these extreme mass ratio inspirals, a small object spiraling into a massive one. QPEs may be their visible counterparts. This is why the eROSITA finds mattered so much. Ricardo Arcodia's team showed QPEs live around relatively small, low-mass black holes, precisely the kind of hosts the Inspiral model predicts. It also reframes what these black holes are. Many QPE hosts sit at the very low end of the supermassive range, bridging toward the elusive intermediate mass black holes, objects we can barely find any other way. The orbits involved are tighter than anything in our solar system. The whole system, a dead star and a black hole, would fit comfortably inside the orbit of Mercury, with a lap time measured in hours, not years. And each collision is enormous. A single eruption can release more energy in an hour than the sun pours out in thousands of years, all from one object slamming through gas. There's another thread here, and it starts with a different kind of catastrophe, a tidal disruption event, where a star wanders too close and is torn apart by the black hole's gravity. Several QPE galaxies show scars of a past disruption. The shredded star leaves behind a fresh accretion disk, new gas for something to crash through. The 2 phenomena kept turning up together. In 2024, a team led by Matt Nickel caught the connection almost live. A star had been ripped apart in a galaxy called AT2019 QIs back in 2019. Roughly 5 years later, that same nucleus switched on with quasi-periodic eruptions. The sequence is hard to argue with. The disruption builds the disk. A second object, already orbiting, begins punching through the fresh debris. And the eruptions begin, a cause and an effect in order. It even hints at what the diving object might be. A star that lost its outer layers in an earlier close pass, a partial disruption, could leave behind a dense core in exactly the kind of tight, survivable orbit the model needs. The unsettling part is that these eruptions are not permanent. When astronomers checked GSN 069 again, the beat had weakened, and for a stretch, it fell silent entirely, as if the disk beneath the whole clockwork had shifted out from under it. They switch on, they switch off. Whatever we're watching is a phase, not a fixture, and the picture still isn't clean. RxJ1301.9 Plot 2747 has been erupting for over 2 decades, far longer than a fragile little disk should last. Some researchers doubt any single mechanism can cover every source we've found. Teams led by researchers like Margherita Giustini and Andrew Mummery have explored hybrids, disk instabilities feeding the collisions, or the orbiting star being slowly stripped a little more on every pass. Others, like Dheeraj Pasham, focus on the timing itself. The eruptions drift, periods lengthen and shorten in ways a simple, fixed orbit shouldn't. The clock is subtly, stubbornly imperfect. Assemble it all, and the leading picture is genuinely strange. A dead or dying star, locked in a doomed orbit, plunging twice each loop through the debris of another star it will never meet. And every collision reaches us across 250 million light-years as a single puff of X-rays. A clockwork built entirely out of destruction, ticking for as long as the disk survives. For now, the extreme mass ratio Inspiral is the frontrunner, but not the winner. We've found only a handful of clean sources, and each new one pulls the theories in a slightly different direction. What's certain is that in 2019, we discovered a new way for a supermassive black hole to speak, a slow, repeating signal from its innermost edge that nobody knew to listen for. The test that could end the debate is coming. If Lisa flies and hears a gravitational wave source sitting inside a galaxy that's also erupting in X-rays, the case is closed. Until then, the deeper question stays open. Are quasi-periodic eruptions a single phenomenon, or several different things wearing the same mask? And if it's one, which of these suspects is really pulling the trigger?